welcome back. Today we're going to be talking a little bit about the orientation of this course. So before we get started, how many of you have had an experience with deep learning? Okay, just a few. All right. Okay, next question. How many of you are from computer science background? Okay, quite a few. How many of you are from other engineering background? Mechanical? All right. Perfect. So there's a lot of there are a lot of buzzwords about deep learning. Large language models, generative AI, NLP, GPT, computer vision, all that kind of stuff. And one of the goals of this class is to give you an introduction to some of those buzzwords and take a look at what those actually are. But the whole field of deep learning has been really gaining popularity recently, and then we get to see a lot of maybe the figure too small, but these are charts showing the gaining popularity of AI and machine learning. So there are a lot of papers being published, like in mechanical engineering, for example. There's been quite a few deep learning related papers out there, and it's been really a hot topic of research. Well, in a nutshell, deep learning is nothing more than just the statistics of steroids. So, we're going to see that the neural networks are essentially just, glorified, regression model with some really simple mathematics that has a, fancy interpretation of being, in resemblance with biological neural nets and things like that. So let's skip through. So in computer vision, for example, people have been using deep learning and artificial neural networks for solving problems like object detection, tracking, human pose estimation. So those are all purely computer vision based tracking of human body movement and whatnot. Large language models at the moment are really popular. So ChatGPT, DeepSeek recently was released. And with those, large language models, you can, do a lot of, a lot of creative applications are possible with those large language models. So you can, for example, let the large language model to write a code for you, or you could also, have the large language models nowadays to, create an Excel. Sort of formula. So instead of having to memorize all the Excel commands and things like that, you can just type num.ai and then just in a natural language tell the AI what to do. This is another really emerging field, generative AI. So these are all AI generated images. They look very realistic and high quality. This is my favorite one. See the Pope with the white puffer jacket, which is not real, but this is kind of the level of realism that you can obtain by using AI nowadays. It's creating a lot of socially a lot of implications. So this is a few years back, back in 2018, where there was a artwork generated by a generative adversarial network. I mean, compared to the most recent generative AI, the quality of the artwork is not that great. But back in 2018, a group of people created an artwork and then actually, submitted to an auction, and then they actually sold the artwork, $400,000 US dollars. And then just after a few years, I mean, this is the quality that we're getting with AI. So, it almost seemed like AI is taking over the world. A lot of people are concerned about AI kind of replacing human manpower, and then replacing a lot of human jobs, right? But is it really the case? So I think a couple of years back, when Google first released Gemini, which is their version of large language model, there was a lot of fun memes like these. So somebody, for example, Googled tell me food names and that ends with and then this is the answer that Gemini came up with: apple, banana, strawberry, tomato, coconut. Coconut is not even known. Or, things like how many feet does an elephant have? And then, the answer foolishly saying elephants have 2 feet with 5 toes on the front feet and 4 on the back feet. Doesn't seem to understand what's really going on. And there are a lot of examples like those. Now, the reason, for being AI, not so great at, making predictions like that is because of the bias in data quality. So, for example, somebody Googled, why cheese is not sticking to a pizza. So somebody, obviously wanted to make pizza, and then cheese was not, sticking to the pizza. And then, the AI overview basically said, oh, to make cheese stick better to pizza, you can add 1/8 of a cup of non-toxic glue into the sauce so that it gives more tackiness. And later on, people actually discovered that there were some Reddit threads where internet full of trolls, right? So somebody just sarcastically replied to one of the Reddit thread, and then said, if you want to get the cheese to stick, I recommend 1/8 cup of Elmer's glue, which is the one of the most popular glue brands in the U.S. We have a Zoom issue.
That also stay like that. After. No, sir. It was a generated.
Sorry about that. Yes, cheese not sticking to pizza, so add glue was the conclusion. Here's another, silly example of, AI doing its thing, so, somebody Googled, for whatever reason, how many rocks shall I eat? And then, the AI response to that question was, according to geologists at UC Berkeley, you should, eat at least one small rock per day. And then, people kind of tracked, where this is coming from. And then, discovered that, there was an article, in the Onion. For your information, this is, purely, prank website. This is, looks like a, regular newspaper, but, this is just for, people, upload some silly articles. And over there, they have this, quote unquote news article, that said geologists recommend eating at least one small rock a day. And then, AI being unable to distinguish the true information versus prank, it somehow learned to, to respond to the question like that. Yeah, so, this is kind of, a problem nowadays. Because AI is becoming so powerful, and then, creating this perception that AI can, do everything. People sort of just rely on, AI without really, thinking through. But then there's this, human knowledge that, has been accumulated over, how many years now. And that's especially the case for, in the field of physics and, engineering, where we've accumulated a lot of, human knowledge, and then all of a sudden we just decided to disregard all the human knowledge and then stick to AI predictions. So it seems like that's what's happening, at least nowadays in many academic journals, for example, where, okay, we're going to solve this very simple problem using deep neural networks. And then, almost, disregard the when you learn from, physics 101, and then just, throwing a bunch of data in the NVIDIA GPU, and then let NVIDIA figure out the solution for you. So I think we're living in a, very interesting time where we're living in a very interesting time where the power of AI has grown to a certain level, but in the meantime, there's a lot of concerns, also. So about a decade ago, when first deep learning came out, there was this tremendous hype. But I think now we're getting into the stage where we start to kind of realize the reality, right? Is it really is artificial intelligence really intelligent? Is the fundamental question a lot of people are trying to ask. And more to the main topic of our lecture series here. When it comes to physical structures and the governing principles, AI algorithms are not that great yet. For example, a lot of image generation algorithms are based on certain pixel combination. Generative AI does not really have an ability to understand the physical structure of, for example, human body. So human hands are very well known to be subjects that generative AI cannot do a great job. So as you can see over here, it created all kind of weird, physically impossible shapes. And if you kind of close up and then look at the a small range, small region of pixels over here, they look kind of realistic. If you forget about the global context, if you just focus on the texture and things like that, they kind of look realistic. But then the overall structure is just just a mess, right? I don't know if you guys have seen this fun video. There's a YouTuber who's been creating TV commercials using generative AI. This is all AI created pizza commercial. And you can see that that problem again. For some reason, if I go over there, might be blocking something. So look at the the mouth of the people and how they, right? It's kind of creepy, So this is all because AI models currently are incapable of understanding the physical structures and the governing principles of physics and things like that. I mean, companies like OpenAI, when they create a generative model, in their case, they can afford like shitload of data, right? Which means that by the virtue of having large number of data, you sort of go around the problem of AI not being able to understand physics. But in a lot of situations, you cannot afford that much of data. So for example, if you're from a mechanical engineering background or a physics background, that how expensive the data can be. So for example, let's say you're interested in I don't know, teaching AI to solve Navier-Stokes equation, right? And in order to do that, you're going to need a lot of Navier-Stokes simulation data. And CFD simulations, right, with a relatively small Reynolds number, relatively easy simulations can easily take several hours. Whereas the real interesting problems, the ones with high-speed fluids and things like that, I mean, a simulation may end up more than a day or even a week, right? To achieve a real stable, high-resolution data, which means one data point may require days or weeks on a supercomputer to generate. And generative AI models, usually require, millions of data points, right? So imagine, as a graduate student or, as a student, I don't know which stage of your career you guys are in, but imagine as a grad student trying to generate millions of, simulation data points, right, to train an AI model. It's going to be impossible. I mean, practically, there's no way you can generate that much of data. And also, if you think about it, this is kind of a dumb, thing to do. I mean, Navier-Stokes equation, you already have the equation. You already have the mathematical formula. Well, why in the world, right? Forget about, this mathematical equation and then, the human knowledge that we accumulated over the past, a few hundred years, right? And then, just rely on NVIDIA GPU to solve that problem, right? So that's kind of a dumb thing, think about it. So that's essentially what is really acting up here. So that is really, the topic of the class for this GM lecture series. So look at this picture. So what do we see right now? You see a car. There's a guy sitting on a washbowl or something, right? Is that a rope? Right. And engine must be on, by looking at the light. And then, there are guys sitting in the trunk, right? With a camera, of course, nowadays. And then there's a bottle of drink. So must be drunk, right? You can guess. So as a human, you sort of, have an ability to understand and parse the information in that photograph. And then you can sort of, predict the outcome, right? Physically speaking. So one possible outcome is, as the car accelerates, right, the rope, it'll yank the rope, right? And then, the human body has a, the center of mass over here, right? So then, this guy may tip over. So concussion is one possible outcome. Another possibility is that the rope is not, doesn't seem to be strong enough, right? So when the rope breaks, then boom, it'll hit the guy in the face, and then that's another possible outcome you can think of. But this is what AI sees on the other hand. As opposed to what we do, understanding and parsing the information and then predicting the outcome based on the physical knowledge that we have. This is basically what AI sees. It simply sees the image as a collection of, bounding boxes, essentially. And then that detection is not necessarily always accurate. So, yeah, I'm basically, keep repeating the same thing, but Leonardo da Vinci, I mean, he's a famous artist, obviously, but he's also contributed a lot to the field of fluid dynamics. And his drawings actually of water flows provided a lot of useful information to the physicists and scientists back in the days. And then, what he did was to, just sit down, nearby the river, observe all this interesting, patterns of water, behind certain intersections and things like that. And then, came up with a lot of interesting observations, alongside exit notes. And then that, back in the days, provided a lot of useful information to the scientists to study the field of fluid mechanics. So, here's the fundamental question. If we have, enough data of some physical phenomena, can we teach AI to learn the physics? Obviously, AI models require a lot of data. So not just one apple falling from the tree, you may need multiple apples falling from the trees. Yeah. Hopefully, we don't really need to, have millions of apples because, like I said earlier, generating simulation data can be very expensive. But somehow, can we teach AI and then have it come up with this, more structured conclusion about certain physical phenomena and so on and so forth? It's kind of, going to be the topic of this class. And hopefully, after finishing the course, you will be able to, play with some, real interesting data. Obviously, we're not gonna, go to, this type of scale. In the class, we're gonna be, pretty much dealing with some toy examples, less complicated problems. But the principles of physics-aware deep learning that you learn from this class will allow you to, easily apply that knowledge to, more sophisticated problems like environmental modeling, for example. Here's another, cool application of using AI. So this is a design tool where you can design a box, I believe. And then, this software is equipped with an AI physics solver, so that in real time, as you change the design, you can kind of, simulate what's going to happen, according to that design change. Again, I mean, if you're from an engineering background, you would probably appreciate this, kind of tool, because the usual process is that you make a change to your design, you have to export it to a CFD solver, and then have to wait for like, several hours to get the result, result to come back. And then that process of converting a design file to a, CFD match is also, very painful to generate. Whereas here, I mean, you can, as you change the design, you can almost in real time see what's going to happen, right, with the change in design. We talked a lot about CFD, so this is, Navier-Stokes solver by using this thing called the NVIDIA modulus. NVIDIA modulus is a Python library by NVIDIA that is equipped with a bunch of physical-aware deep learning models. And using NVIDIA modulus, for example, you can, develop your own Navier-Stokes solver so that for a given, change in the boundary condition, you can simulate the fluid behavior without having to wait for like, several hours. This is almost, instantaneous prediction of fluid in the changing the gear a little bit, biomedical application is also where physical-aware deep learning can be useful. So this is cardiac electrophysiology example where, you're basically interested in the electromagnetic field on the surface of the human heart. And then, previously, people had to solve, the Maxwell's equation to produce a exact simulation of the electrophysiology. But now with the deep learning model, it takes 0.16 seconds as opposed to the previous 2 hour of simulation time, so that you can almost instantaneously take a look at what's going to happen with the cardiac physiology. Here's a similar example, but applied to human brains. So again, there's lots of going on the human brain, which is governed by, some, electromagnetic fields, in the human brain. And again, neuroscientists, they've been simulating, the dynamics of, brain activation, using, physics-based simulation solvers. Versus nowadays, you can use machine learning models to make predictions. This is a little bit of my research research work. So one of the things that I'm interested in are explosives and bombs. So that's what Americans love to do. So bombs, fireworks, those kind of things. And at the microscopic level, you get to see a lot of microscopic structures like those. So those are the pores, and what happens is when a shock is applied, the pore kind of collapses and then generates high chemical energy, which are called the hotspots. And then what I'm interested in is the pattern of the hotspot generation. Okay. As a function of the microstructure geometry. So as you can see, different pore shape will create a different patterns of hotspot, after a shock. And then understanding this is of critical importance for the design of better energetic materials, and so on and so forth.
Is that dynamics, Professor? You call it pore shape.
Yes. So those are, cracks inside of the crystal, or also, sort of a gap between, energetic crystals and things like that. And then usually those kind of high heat is generated at those, imperfections. And understanding, how they respond to external shock is what people have been working on. Back in the days, to run this kind of simulation, you would need about a day on a supercomputer. Because this is a very, like extreme dynamics. All of this happens in a few nanosecond scale. And then in order to obtain a stable simulation, you would need to, resolve it in a very fine grid. And then running a simulation like this would require about a day. Versus with the machine learning model, you can achieve a pretty good accuracy, but with less than a second of computing time. So that's kind of the newest trend in material science. Here's another cool application. So this is another American thing, football. This is obviously the favorite America's pastime, but this is one of the sports where there's a lot of injury happens. So I've been helping NFL to develop computer vision, tools to track the player movements and then analyze what's causing injury and things like that. Any questions so far, by the way? Good, all right. So, like I said earlier, AI models does learn physics from data if you have large number of data. But in most of the cases, this is something that we cannot afford. So these are, OpenAI video generation algorithm, Sora. And if you look at the snowflakes and then, the reflection of the road on the video on the left, I mean, they all kind of look, very realistic, right? And physically, plausible. But in their case, they could afford the large, amount of video data. And then they had a, super, fancy computer to process all that data. Whereas in our case, we cannot just simply fit the model because we have limited data, because we don't have that big of a computer, and also we would like to leverage some of the, previous knowledge about, physical phenomena. Instead of just throwing everything, into NVIDIA GPU. So here's, a fun, one example to think about. F equals to ma. So probably everybody knows what this is, right? You apply a force to a mass, and assuming that there's no friction, right, that mass will, develop an acceleration as a response to that force input, right? So, let's say you're designing a machine learning model to predict the acceleration, given force and mass. Okay, and let's pretend at the moment that you know nothing about Newton's physics. Okay. So, of course, since you already know the second law of Newton, you know that the acceleration would be the function of the force divided by the mass of an object. Right? So this is kind of what you will see as you plot, mass, force, and acceleration as a chart, right? So we have two inputs, force and mass, right? These are the things that we vary. And then as a result of that, we want to predict the acceleration. And according to that analytic formula, this is going to be the chart that we'll see. Now, since we already know the ground truth, what we can do is to generate lots of data. Sorry for people who are sitting behind, but you can write a simple Python code to generate a bunch of force values. You could generate a bunch of mass, and then from there, we know the acceleration is force divided by mass. And then to emulate the real world situation, we add a little bit of noise to the acceleration, which I think is fair, right? Now, based on the data that we generated like that, let's try to fit a neural network. Okay. For those of you who are not, already familiar with the neural network, that's fine. We're going to get into the details, later in this class. But essentially, consider some, mathematical model, right, with some parameters that you can tune, right, and then you want to figure out the relationship between mass force as an input and then acceleration as well. And this is the result that you get. So on this chart, we have the true acceleration on the horizontal axis. And then we have a model predicted acceleration on the vertical axis. And obviously, if the model is perfectly accurate, then all the predictions should be on this diagonal line. But it turns out the performance of the model quickly degrades as it goes beyond what's covered in the training data. So on the training data, it does a fairly good job of predicting the true acceleration value. But beyond that range that's been covered by the training data, we're seeing this kind of weird result. You may wonder why, because this is not even a complicated physics, right? We have pretty much high school physics. There's nothing interesting going on, but still a neural network is unable to physics very well. So you may wonder, what if I make the model more complicated? So this time, in the previous example, we had a neural network with 8 neurons, but now I increased the number of neurons to 256. Would this do better? Well, it turns out, we still have a very poor prediction result, even with a wider model. Of course, we could go deeper. So instead of one hidden layer, you could have multiple hidden layers and see if we can, do a better job. But still, this is kind of the result we get. By the way, if you know how to, program neural networks, I would strongly encourage you to, do it yourself. because we'd be fascinated by how poor the neural network is in learning such a simple problem, like ethics that make. So with that as a motivating example, the plan here today, I mean, not today, but for this this course, is that we're going to be introducing the neural networks and what's called the convolutional neural networks. And then we'll also introduce what's called PyTorch. PyTorch is a Python library for programming neural networks, leveraging, the hardware accelerators, like NVIDIA GPU. So that's the plan for pretty much the first week, which is to introduce neural nets and how to program using PyTorch. And then we're going to be having some fun time with 4 different types of physics-aware deep neural networks. Okay. The first thing is what's called the physics-informed neural nets. This is probably the one that has been most popular in the applied physics community. We'll also take a look at this thing called the neural operators. And then there's this physics-aware recurrent convolution, or PARC, is another topic that we're going to cover. And then we're going to see how different, physics-aware deep learning models incorporate physics information during the training process. So they have, subtleties in terms of how they incorporate physics information. And we're going to take a look at those differences. We're also going to see a reduced order modeling. So, if you're from CS background, this is kind of, dimension reduction type of a deal. If you're from an engineering background, you probably know what reduced order models are. So, imagine you have some high dimensional complicated physics data. What if you can, map that high dimensional complicated physics onto relatively low dimensional space, and then learn the physics in that low dimensional space is kind of the idea here. And then if the time allows, we're going to do the generative, neural networks a little bit, and then see, the topic of digital twin generation, and so on and so forth. But I plan to be a little more flexible in terms of the schedule. I think the most important thing is for you guys to, take away with necessary knowledge. And the skill sets to explore this field, as opposed to just, I don't know, injecting everything in such a short period of time. So I'm going to be a little flexible in terms of the schedule. If you follow the contents well, then I might speed up a little bit. But knowing that we have a very diverse group of students, I'm going to be also mindful of different backgrounds, especially when we introduce neural networks and such. So in terms of the prerequisite, I'm going to assume that you already know some programming, preferably Python. Okay. Well, so Python programming is a prerequisite for this class. But if you have some level of familiarity with MATLAB or C++, that should also be fine. So any sort of programming language, as far as you know, that should be fine. But if you have never coded anything in your life, then this might be a little tough. But if that's the case, please feel free to let me know. I'll be happy to check. Multivariate, vector calculus and linear algebra. Knowing that we're in India, I guess I'm not going to worry about these mathematical concepts. Basic understanding of differential equation is another thing. Again, I know that Indian students are very good at math, so I guess I'm not going to worry too much about it. The level of differential equation, I'm not, expecting, a very deep knowledge. As long as you understand what, gradient is, divergence is, cone is. And then as long as you can sort of, intuitively say, oh, this equation over here talks about, time derivative of some sort, blah, blah, blah. That should be fine. I'm not gonna look for you guys to solve, for example, partial differential equations using hands, which is impossible for most of the cases. So don't worry too much about it. Another thing is, we're gonna be doing a lot of in-class activities. So if you brought your laptops, that's fantastic. If you don't have a laptop, then you probably want to, sit next to somebody who already has a laptop. We're gonna be doing a lot of Python programming. The easiest pathway is to use this thing called Collaboratory. Have you guys seen this? Yeah, okay. The Google Collaboratory is a very nice, free tool. If you have a Google, Gmail account, you can have access to this. It's under Colab, colab.research.google.com. If you go there, you can have access to a Python development environment. And then Google provides a free, computing resource. So even if your computer, for example, does not have a, fancy NVIDIA GPU, you can still use Google Colab to, train a neural network and so on and so forth. So this is probably the easiest way to get started. So if you have no, Python background, no previous experience with deep learning, this is probably the easiest pathway. Zoom. Lot of signal or something. It's all fixed now, so. So yeah, so Google Colab is what we're going to use. All the course materials are available on in my GitHub repository. So it's under github.com. Stephen Beck, my name /PADL paddle. And if you go there, you should be able to access all the lecture slides and course materials. The lab sections are essentially the ones that will use Google Colab. So if you, for example, click this one, Introduction to PyTorch, which is something that we're gonna do in the in the next day or so. If you just click Open in Colab button, this will just automatically direct you to a Colab version of that, from which you can just, you know, run the code. It's a little bit of time when it's first loaded up, but once it's loaded up, yeah, there you go. So without installing anything, you can access this from your web browser. So it's probably the most pain-free way of getting started. And then, you know, you can play with PyTorch by running this code. It's all very interactive. So you know, if you have, you know, have never used Python or have not done anything too much about deep learning and PyTorch, this is probably the easiest way to get started. If you are more experienced and wants to, you know, run this code on your local machine, so in my case, I'm not actually going to use Google Colab, but instead use my own laptop to run the code. And if you want to do the same, I put a tutorial on that GitHub repository in terms of how you can install Python, how to configure your environment, and so on and so forth. So hopefully by going through this step-by-step instruction, you should be able to configure PyTorch and Python on your local machine, and you should be able to run the code on your local machine. But that's, I guess, only for people who already have some experience with Python. If you're new, this might be a little finicky to configure. So yeah, that's one of the things that we're going to be doing. Yeah, I guess that's really it. Any questions so far? Yes.
For the last example that you were talking about, so do you always assume a normal distribution, or and how do you know how much data is needed in the sample for the level of confidence that you're expecting?
So on your first question, the you don't always assume normal distribution. Although you know, without, I don't know, any assumptions, normal distribution is probably the easiest you know, random distribution that you can begin with. But different physical problems may have different, you know, distributions. So it's not always, you know, necessarily a normal distribution. And what was your second part of the question again?
For a certain confidence level, can I compute the sample size?
Oh, yes, yes. So that's also another very common question about deep learning, like what's the appropriate sample size and how do you guarantee certain confidence level? In the traditional, you know, statistics, there are ways to compute the, you know, determine the n, right? Deep neural networks, it's sort of, I don't know, all this traditional statistical knowledge of determining n and the confidence interval no longer is valid because we're talking about models with millions of parameters. And then, you know, if you put million in, in those, conventional stat formula. None of this started to make sense. So unfortunately, there's no rigorous answer to that. It's usually just the more the better. But we'll see that a lot of physics aware models, you can start training those models with as small as 20, 30 samples. That's one of the virtues of physics aware models. If the model is not physics aware, then you're going to need way more data. Versus if you have a model that is physics aware, then as small as 20, 30 samples, you can start training the model. But again, there's no rigorous answer as to how you determine the number of data necessary to have certain confidence in prediction. There's no rigorous answer. Yeah, that's a very good question. Other questions?
Precision control.
Well, it's been doing this
One second.
the whole time. So
Wi-Fi is becoming. Input is and for passing a connection.
all right, do you guys want to take a quick break before we resume, or are you ready to jump into the? Ready. You ready? Okay. So intro to neural nets. This is the session for people who does not have a previous knowledge on neural networks. But this could also be a good kind of a refresher for probably CS students who already know neural nets. So let's start with this motivating example. So when we talk about machine learning, we talk about the problem of finding a function f that takes certain input x and then predict output f of x that hopefully is as close as possible to a ground truth data y. So a typical machine learning task is comprised of a data set. So when we say a data set, it's usually a pair of input and output. Okay, and then for the input, we assume that there's some input x, could be a vector, could be an image, could be anything, and then y is the corresponding output to that x. So if we're, for example, talking about a physics problem, I don't know, this input x could be an initial condition or some physics parameter, right? And then y could be the system response, right, to that initial condition and physics parameters. For image classification application, as another example, x could be an image, right? And then y could be the label associated with that image. Actually, we're going to talk about that in one of the lab sessions. And then a machine learning model is essentially a function f that is parameterized by some model parameter theta. Okay? So theta is what defines the function f. Okay, so polynomial regression, right? As an example, in that case, function f is as, some polynomial function, right? With coefficient theta, right? And then, your goal is to fine tune theta, right? In such a way that, after finding an optimal configuration of theta, then, as you throw in an input, then the function f will spit out an output that is as close as possible to the ground truth, right? So, like I said, examples. Let's say, you're a civil engineer who, is interested in, predicting permeability of certain, mixture, of particles. So in that case, the input x could be defined as a vector comprised of, say, particle size, void fraction, porosity, fluid viscosity, blah, blah, blah. And then as an output, you want to predict the permeability of that configuration. Or, let's say you're interested in detecting damages in some structural component. You may want to fly a drone, right? And then, take photos of certain structures. In that case, the input to the machine learning model could be an image, right, coming from the drone. And then the output is crack versus no crack, for example, right? So that is really what we call machine learning at the end of the day. So how do we find theta is essentially the question that we encounter when we train a model. So when you consider a linear model, okay, a linear model is a model where we don't have higher order terms, right? So let's say, your input x is, well, I have a word I have for d minus 1 dimension, but anyways, let's say your input x is d minus 1 dimension. And in that case, a linear model could be, simply just a, weighted sum of those d minus 1 dimensional vector, right? Vector components alongside the, scalar, y-intercept, right? And then in a vector representation, this could be simply just x transpose times theta or x dot theta. And then, what you want to do in the vector representation is to minimize this loss function, which is y minus x theta squared, where the capital X is a stack of those row vectors, right? And then the boldface Y is a stack of the ground truth labels, the ground truth values, right? And the solution to this, if you're familiar with the the pseudo inverse or these square problems, we know that I'm not actually gonna go through all the derivation, but we know that the optimal theta can be determined as the pseudo inverse of x times y, right? Or x transpose x inverse times x transpose y. So in case of linear models, you can analytically derive the optimal solution for theta. So which means given x and y, you just throw that into this this formula. And then there you go. You have the optimal, theta as an output. However, if you have, nonlinear, if you have a nonlinear model, so for example, for whatever reason, your fx is comprised of cosine and tangents. Okay. I mean, the moment you start to have nonlinearity, finding the optimal solution is not, very easy, right? In most of the cases, you may not even have an analytic solution for the optimal solution. So this is why in machine learning, especially in neural network literature, we use this strategy called the steepest ascent or gradient ascent. Or in case of minimizing, we're doing the steepest descent going down. So the idea of a steepest descent is as follows. Imagine you are trying to climb up a mountain and you want to reach to the peak, but let's say your vision is very limited. So you don't really see the whole mountain, but only your surroundings. So in that situation, probably the best strategy to get to the top of the mountain is to look around you, right? And then whichever direction has the steepest increment is going to be the direction where you make a next step, right? And then you basically repeat the same thing. You look around you, and then whichever direction gets you the steepest descent, you make another step, and so on and so forth. And as you repeat that, step by step, hopefully you will get to the peak of a mountain. It's kind of the idea. So mathematically, we're going to define that strategy using mathematical terms. So again, we start from some initial theta 0. And then iteratively, we want to, go up the mountain. And then hopefully at the end, we'll get to the top of the mountain. Now, the steepest direction, okay, in that mountain defined by some mathematical, loss function L, is essentially the direction of the gradient. Okay, so the idea of gradient of a scalar function is the direction which the function value changes most significantly. Okay, so by computing the gradient of that loss function L at the location theta that you're in, you should be able to find the direction where the function value increases the steepest. Okay. Now, with that, this is really the mathematical representation of what we just described. Okay. We update theta. Okay. So starting from an old theta, we update the theta to get a new theta. Okay. By adding to that old theta value by some factor of the gradient. Okay. So the gradient vector, like I said, is the vector indicating the steepest descent, right? And then we're basically, following the direction of that, gradient to maximize the function value. So that's really the idea of a steepest ascent value in case we're maximizing the function. A lot of times we're minimizing the loss function. So in that case, it's just the minus sign attached to that gradient term. So instead of following the direction of the steepest ascent, in case of minimizing, we just go in the opposite direction, right? So by considering a minus sign. So that's really what we can do to minimize some complicated function. And this is a strategy that known to be quite effective for many of the nonlinear functions, including neural nets. So if you think about it, this is a very simple strategy. There's no complicated terms or anything like that. As long as you know how to compute the gradient, which we're going to talk about soon. But as long as you know how to compute the gradient, you should be able to compute this pretty easily, right? There's no higher order terms, for example, that requires a lot of computation. You just need to compute the gradient and then add that gradient to the theta value, and then you just repeat, right? So it's a very, very simple strategy, but very effective. Now, before we talk about the actual details, using the gradient descent algorithm this is essentially, the strategy for training a machine learning model. So the first thing, to do is to design your model F, okay? And, define the training objective. And the training objective is usually, represented in the, in terms of, loss function. So, the most typical training objective might be to minimize the prediction error, was the case for, the loss function that we saw, a few slides ago. And once you have the model and the training objective defined, then the next thing you want to do is to initialize the model parameters, okay? And then run the gradient descent. So start from some random data, right? Evaluate the gradient and follow along the direction of the gradient. And that's going to be the new theta. And at that new theta, evaluate the gradient, follow along. And then as you repeat that process, you should be able to, converge to some theta, okay? And then that theta is essentially the optimal solution that you're looking for. So at the high level, it's a very simple process, right? You start with some model and some training objective, and then essentially just keep evaluating the gradient, make a step, evaluate the gradient, make a step, is essentially what we do. Now, designing the model. That's something that we haven't talked about yet. And especially in this class, we're going to be talking about neural networks. So there can be many, different options, for your machine learning model. But in this course, we're going to be dealing with, mostly neural networks. So let's talk about that first. And then later, we're going to revisit this idea of evaluating the gradient. And then by that time, we should be able to complete the full picture. Okay. Any questions so far? This.
The scalar value, in a practical situation, how would you guess it? Is it something you?
Which scalar value?
The alpha.
Yes, we're going to be talking about that. So that's what's called the learning rate. The reason why we have that alpha is to compensate the numerical instability. So if you just naively follow the gradient, then likely because of the numerical instability, your solution will diverge. That's why we multiply some small value alpha. How we determine that, we're going to talk about that later.
And the initial theta value. Suppose you have some gut feel about the problem you're solving. Then you don't need to go with start with some random guess. Let's say you know some ballpark.
That's a very good question. So usually you start from a randomly generated data. But if you already know about the problem and if you already have some model, then there's a way to start with some predetermined data value, like you said. And that way you may be able to converge faster. So again, for that, we're going to be talking about, how to determine the initial, value of data in the later class. Great question. Any other questions so far? All right, cool. So neural nets. It seems like about half of the class already know what neural nets are, whereas the other half is still kind of new. The idea of neural nets are often, associated with biological neural networks. So in human brains, we have, a bunch of neurons, right? In fact, we have lots and lots of neurons in our brain, and then they somehow, fire up a signal, and then our brains somehow, process all these electric signals, right? And probably from, high school biology, I guess, right? Or college. I think it's high school biology. Yeah, you learn about the anatomy of, neurons. So a neuron is comprised of the soma, the neuronal cell body. And then the cell body is has lots of antennas, okay, called dendrites. And those dendrites receive signal from other neurons, okay, and those signals received from the other neurons are somehow aggregated, right? And then that aggregated information gets passed along through what's called axon. And then the axon, the tips of the axon is connected to, the dendrites of the other, neurons, through which you can, pass along information, right? So the idea of artificial neural networks is to mathematically model this process. Of course, we're going to introduce a lot of assumptions. So we started with this very ambitious plan of mimicking the human brain. At the end, you will see that this becomes a very simple mathematical formula. But let's say we have n neurons that's connected to the current neuron, okay? And then the signals coming from the other n neurons, we're going to represent them as x1 through xn. Those signals are somehow aggregated, okay, in that the cell body. And here, we're going to assume that they're linearly aggregated, which means we're basically taking the linear weighted sum of x1 through xn. So the weight values w1 through wn are the weight values to, disproportionately, count for the other signals, right? And then that gets aggregated via weighted sum, which is then passed along, okay? And then before it gets passed along, we have this notion of activation function or transfer function. The idea of this is to kind of cut off the signals that are, too weak, or to kind of saturate the signal. So if you poke a person in front of you, right, in a very gentle push, then at the beginning, the person in front of you will not recognize, right? But then as you increase the strength of that poke, right, the person in front of you will start to recognize that you're poking at, that person, right? And then the sensation that the person in front of you will feel will kind of proportionally increase, right, as you increase the strength. And then at some point, if you hit the person in front of you really hard, right, they will start to feel the pain, but then that pain will no longer grow proportionally. You know what I mean? At some point, it's just a pain, right? You don't feel a stronger pain, even if you hit the person harder. So that's kind of the idea of activation function or transfer function. So at the beginning, when the signal is weak, you're basically cutting that off and then ignore that signal. And then beyond certain threshold, now there's a zone in this function where the strength of the input and the strength of output will be proportional to each other. And then at some point, you don't feel anything. It's just numb, right? So that's kind of the idea of activation. We're going to talk about that later, more in detail. But after that, is what we call the output of that neuron. Okay. And that output is going to be then passed along to other neurons. Okay. So the output of the current neuron will become the input to other neurons. And then basically we're passing along this information using these artificial neurons. So with this simplified model, what we have is essentially a sort of a linear equation. Okay, we have the weighted sum of the input signal xj, right? So we're taking the weighted sum of those inputs, which then get passed along to the activation function, which I denote as sigma. Okay, and then that sigma of the weighted sum is essentially what defines an output of the neural network. And, you know, because we have indices that pairs up, we can write it down as a matrix formula, right? So instead of Wij times Xj and then take the summation, blah, 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 you could just simply write it down as, you know, matrix X times matrix W, right? Which then goes into the sigma, the activation function. And then as a result, we have the output Y, which is a vector. A little bit more about the activation and the transfer function. So like I explained, it's basically the idea of threshold and the saturation in biological systems. At the very beginning of neural nets, back in 1950s, people actually used this, you know, step function as an activation. So there's actually no, you know, proportional increase in pain, right? It's just either 0 or 1, okay? So if it is beyond certain threshold, it's 1. If it is below certain threshold, it's 0. But then one of the problems with the step function is that it's not differential at 0, x equals 0, right? And since this is not differentiable, we're going to see that you know, there are certain downsides of using this step function, especially when we, you know, train the model. So instead, you know, people came up with this thing called the sigmoid function, which is kind of a smooth approximation of the step function. Okay, so it kind of looks like a step, you know, step function, right? In the sense that, you know, beyond certain threshold, we have 1, and then below certain threshold, we have 0, but we have a smooth curve in between, so that it is differential. So the simplest model is what's called the perceptron. So Dr. Frank Rosenblock was a researcher at the Air Force Office of Scientific Research in the United States. And back in the 1950s, he came up with this idea of perceptron. And the perceptron is essentially what I just told you. So again, we have x1 through xn. Those are the signals coming from you know, other neurons. Okay? And then that gets aggregated, okay, at the cell body, alongside a term called bias. You can consider this as a y-intercept in a linear model. So that's that. And then, like I said, Rosenblock's initial perceptron model used to have this step function as an activation. And then at the end of the step function, we have the output Y. So that's really the mathematical representation of the perceptron. Again, we have the weighted sum alongside the bias term, right? Which is then, you know, which then goes through the step function, the binary step function, and then that's what determines the output. Obviously, for the perceptron, we want to minimize the discrepancy between the model prediction versus the ground truth. So let's say the ground truth in our data set is y hat, whereas the model prediction is y with I hat. And then what we would like to do is to minimize the difference between the ground truth and the model prediction, right? So we have this simple, you know, least squared formula. And, you know, the gradient descent algorithm, essentially, where, you know, we evaluate the gradient of this loss function, the training objective. Okay. And since we have a step function as an activation alongside the, you know, essentially a linear model with a few, you know, minor calculation, you should be able to obtain this, okay, as a gradient value. At the end, all this, you know, all this, you know, gradient, term boils down to the difference between the ground truth and the model prediction multiplied by the input, XJ. Okay, so that's the gradient of that training objective. And then this is the gradient, descent formula, where we update the weight value W, okay? So the weights W1 through WN are the parameters that we can tune, right? And then they can be tuned by using this gradient update formula. The alpha term, or here, I just used R as a learning rate. So this learning rate is the term that we introduce to make it less sensitive to, certain numeric noise. So can you guys guess what so this is obviously Frank Rosenblatt. But can you guys guess what this thing is over here? Transistor,
Why or diode, some diodes?
diodes, yeah, good guess. That's actually a camera. Yeah. So, we have a camera that has, 20 pixels by 20 pixels, a total of 400 pixels. For your reference, iPhone, you have like 13 million pixels or something like that, right? So, but back then, it was a, 400 pixel camera. So in terms of the resolution, it was horrible, right? You couldn't see anything. This is essentially a camera that is comprised of what's called a photocell. So photocells are, the electronic components that produce a voltage in response to certain, light. So if you have a stronger light, the photocells will produce a, larger voltage. If you have a, dimmer, darker light, then the photocells will produce a lower voltage. And in that way, right, you can have sort of an analog image, comprised of 400 different voltage signals. Right? And what Rosenblatt wanted to do was to develop a image classifier. How fun, right? So this is the perceptron, that mathematical model implemented in an electric circuit. Yeah, so it was a giant machine, taller than myself, comprised of lots of wires, okay? And what he did was to basically connect all the wires to those 400 pixels, okay? So the photocells will produce the voltage signals, right? And that voltage signal will be passed through those wires, right? And then at the end of those wires was a potentiometer. You know what those are, potentiometer? The variable resistance. Yeah, so by turning the knobs of the potentiometer, you can basically control the electric current, right? So same voltage, different, resistance, you'll have different current, right? So that's essentially how he implemented this. Okay, so the weights, okay, the one that controls the strength of the signal is controlled by the potentiometer, right? And your job is basically to turn the knobs of the potentiometer, right, until you have an image classifier that does a fairly good job. Does that make sense? Yeah. Yes. So this is it. This is really the physical implementation of the perceptron. And obviously, this was a big, thing back in the 50s. People got super excited about it. Because of this idea of classifying images using machines. It's kind of looked like a human, a geeky, human brain with lots of wires and things like that. And the image classifier that he developed worked quite well. Obviously, it required a lot of time and effort to train the model. Because, right, imagine yourself tuning the potential, according to that gradient descent formula, right? So what you get to do is to present an image, right, in front of the camera, And then the perceptron initially, initialized with some random weights will produce some random output, right? And that random output will be different from the actual, ground truth of that image. And that difference will inform you which direction you have to turn the knob, right? And then you repeat that process like, thousands of times, you get the model. But after the training, it worked quite well. And, this is probably the beginning of what's called connectionist machine learning models. But then people kind of realized that, even though, if you just look at the machine, it looks super complicated, right? With lots of wires and lots of, electric components. But at the end of the day, people realize that this is really just a linear binary classification. Okay. So remember, the activation function for the perceptron was a step function. So, which is the function that returns either 1 or 0. And what goes into that activation function was that linear summation. So that's Z, right? Which is the linear summation. So what that means is we have the equation of line, right? Z equals to this is simply just equation of line or equation of a plane, right? Hyperplane in the n-dimensional space. And then, it's either 1 or 0, which means, if something is above that, line, we get 1. If something is below that line, we get 0, right? So, the problem of, let's say, classifying cats versus dogs, right? You're basically drawing a line, right? And then saying, anything that's above this line will be dogs. Anything below that line will be cats. Okay. Excuse me. Now, perceptron being a linear binary classifier, there were some problems. Okay, one of the problems was this thing called the XOR problem. XOR problem is a toy problem for machine learning people, which is defined as a problem of classifying 2 inputs. Okay. The 2 inputs can be either 1 or 0, okay? And then the output is, this explosive OR problem. So when, the 2 inputs are the same, so either 0, 0 or 1, 1, the output should be 0, okay? When the 2 inputs are different from each other, so either 0, 1 or 1, 0, then the output should be 1, okay? And, the goal of the XOR problem is to build a classifier that can classify those X1, X2 inputs and then produce the correct output 1. Now, can we implement XOR gate using perceptron? Well, the answer is no. Because practically speaking, this is the XOR problem. Okay, again, when we have the inputs that are the same to each other, so either 0, 0 or 1, 1, we have to return 0, okay, which is color coded as red dots. When the inputs are different, so 1, 0 or 0, 1, the output should be 1, okay, which are color coded as green dots. Now, can you draw a line, a straight line, to separate the green dots from the red dots? No. Okay. So that was really the criticism about the perceptron. If perceptron is really, something that is, truly intelligent, and then really mimics a human brain, the perceptron model should be able to solve this simple problem called the XOR problem. But as a matter of fact, you can theoretically show that perceptron will never be able to solve this problem. Okay, and it took about a decade for people to actually realize that perceptron was nothing more than a binary linear classifier, and then it could have solved a simple problem like XOR. So that discussion was in this, a very famous book called The Multi-Layer Perceptron by Minsky and Pepper. And Minsky and Pepper, criticized the original design of perceptron, saying that perceptrons are, binary linear classifier and cannot solve such a simple thing like excellent problem. And instead, they proposed this thing called a multi-layer perceptron, which is, as the name indicates, it's a stack of perceptions. Okay, so we have a perceptron that produces an output, which then becomes an input to, another layer of perception. So, in the original, Frank Rosenblatt's model, all the input come in, and then you just produce one output. In the multi-layer perceptron, we have inputs coming in, and we produce multiple intermediate outputs, which then becomes an input to another perceptron. Okay. And by stacking them up, Minsky and Pepper show that you could actually build a nonlinear classifier that can solve much more complicated problems. So that was 1969, about a decade later, since the introduction of perceptron. This was all great, except that back in the technology of 1960, there was no way to solve this. Okay. So they were able to criticize the original perceptron model and then propose a new model. But in terms of actually training this model, they couldn't propose a solution. So if you think about it, here we have the first layer of perceptron, right? Again, linear sum followed by an activation to define the intermediate output H high, which then serves as an input to, right, the second layer of perceptron. But then in terms of, the gradient of that training objective, now that we have two layers of perceptron, it becomes much harder actually, or I think it's impossible to derive a gradient without using some numerical method. So that was kind of the devastating, limitation of multi-layer perceptrons back in the 60s. And that's when what we call the first AI winter happened. So with the introduction of perceptron, especially U.S. military got very excited about AI and machine intelligence, right? And then they poured in a lot of money to facilitate AI research back in 1950s and 60s. But then after people realized, perceptron was nothing more than a glorified linear classifier, and then especially with this Minsky and Pepper book, people kind of realized the limitation of AI, and then it became the first AI winter. Fast forward into the future, in 1986. A group of people named Ronald Hart, Hinton, and Williams came up with this idea of backpropagation. Okay? And backpropagation is an algorithm that you can use to compute the gradient of a complex function. And this is the algorithm that we still use to train neural networks. So we're going to be talking about that quite a bit in this class. So the idea of backpropagation is as follows. When you have a some mathematical equation, okay, what you do is to break this down procedurally in terms of how the numbers are computed. So let's consider this example of computing x plus y times z. Okay. Procedurally speaking, you first add x and y, right? And then the result of that x plus y addition gets multiplied by z. Graphically, you can represent that procedure as a computational graph, where we have x node, y node, which is then connected to the addition node, right? And the addition node will produce the intermediate output Q, which is the addition of X plus Y. That gets combined with Z at the multiplication node, okay? And the values of Q and Z get multiplied by each other to produce the final output F, right? Now, once you have that computational graph, then you can flow numbers through that computational graph. So that's called a forward pass. In the forward pass, for example, what you can do is to flow particular numbers. So in this example, let's say we have -2, 5, and -4. -2 and 5 gets added, so the Q value becomes 3. And then 3 gets multiplied by, -4, and then the value of F becomes -12. Now, the fun part begins here. When you do the forward path, okay, we're gonna make a little bit of tweak to the forward path. When we do that, we're actually going to compute the local derivative, okay, of the addition node and the multiplication node. And then we're gonna store the values of the local derivative. So here's what I mean. So we have, the Q, which is the output of the addition node, right? Defined as X plus Y. Now, the local derivative, so the immediate output Q, okay, derivative with respect to the input X, which is dq dx, right? dq dx, theoretically, no matter what the input X and Y might be, theoretically, dq dx is always 1, right? And in the same reason, dq dy is always 1 as well, no matter what the input value of X and Y might be. So for the local derivative of this addition node, we know that dq dx equals to 1, dq dy equals to 1. So for the addition node, we have nothing interesting. The multiplication node, here we get Q and Z multiplied by each other. Now, in case of the multiplication node, df dq, so the derivative of the output with respect to the first input, right, is Z, which is another output, another input, right? And then df dz, okay, derivative of the output with respect to the second input, is the first input. Okay. So, using this fact, we're going to modify the computational graph, okay, as we go through the forward paths. And save the local derivative as we go through the forward paths. So what's happening over here is -2 and -2 and +5 goes into the addition node. And we already know that the local derivatives are 1s. And then the result of the computation, the addition of -2 and 5, is 3. So we save those numbers, okay, on this addition node as we go through the forward paths. And same thing, when we go through the multiplication node, we not only compute the result of multiplying -4 and 3, which is -12, but also we store the local derivatives. So in case of this path, the local derivative is -4. And in case of this path, the local derivative is 3. And we store that information in the multiplication. Does that make sense so far? Yeah. Now, after you store these values, when after we store these values, you can use these values to compute the derivative of f with respect to the inputs x, y, and z. And that process is called the back propagation. So To do that, what we do is to start with one, okay? And that one gets passed along to the multiplication node. And when we do that, so from the multiplication node, we can either go up or go down, right? The path of going down, we multiply one by the number that we stored at the bottom. So 1 times 3 gets passed along, and that is what defines the derivative of f with respect to z. When we go up, we do the same thing, but this time multiply by the number defined on the top. So 1 times -4 is -4, and that gets passed along in the backward path. And then -4 again gets multiplied by the number stored in the nodes locally. And as a result of that, we have, the final values -4, and 3 on each node. And those are the actual derivatives of f with respect to x, y, and z. And proving that, those are the actual derivatives is quite easy because we have a very simple problem. Yeah. So if you're new to, the idea of backpropagation, this might sound like, I don't know, cheating. There's no way this can work, but in fact, the idea of backpropagation is based on this, this thing called chain rule, right? And you learn from, calculus, where, you start with the derivative of f with respect to z, and then as you go downward, you multiply this guy with the number that is stored at the bottom. So you have partial f, partial y as a result. And then when we go up, we multiply this guy with the number stored at the top, right? Which is, partial f, partial x. And if you think about it, this is, exactly the chain rule, right? So we're not, inventing anything new, as a matter of fact. We're just, operationalizing the chain rule, okay, by breaking down a mathematical function into computational nodes. Okay. So in terms of the terminology, we're going to use the term upstream, downstream, because the computational graph gives you a visual of, flowing the numbers, right? Flowing down a number. So upstream gradient, downstream gradient. We're going to use the term local gradient. Local gradients are the numbers that are stored in the node, right? And then what chain rule says in this context is simply that the downstream gradient is a multiplication of the upstream gradient and the local gradient. Okay? All right, here's another example. This time a little more complicated, right? So x plus y times z, right? Too simple. Let's consider this slightly more complicated example, where the function f is defined by 1 over 1 plus exponential of negative of w1 x1 plus w2 x2 plus b. The computational graph, well, this, by the way, is the perceptron with a sigmoid function. But the computational graph of this guy, okay, if you think about it, will look like this, where when we do this computation, we first compute the numbers inside of the parentheses, right? So w1 x1 gets multiplied by each other, w2 x2 gets multiplied by each other, and then we have b, and then they get all added up, right? That's what's in that parenthesis. And then we got to put the minus sign over here. So we're going to multiply by -1, the negation node, followed by an exponential node, right? Followed by a node where you add 1, right? and then, followed by that, division. And that's how we define the function f. Now, in the forward path, what we do is we start with some numbers as an input. Okay, and then as we, pass along those numbers, we not only compute the result of that operation, but also, the local derivatives. So I'm not gonna bother to, to actually calculate, all this. But, this is what you're gonna see if you actually, compute the values. Now, when we back propagate, okay, we always start with one. And that one gets passed along, okay? Now, the one over x, we know that the derivative of one over x is,
-1/x².
yes, right? So we know that the derivative of one over x is negative of one over x squared, right? So what happens here is, this one gets multiplied by this value over here, which happens to be, negative of 0.53. Okay, so that result of multiplying one by this is passed along, okay, to the downstream. Now, same thing, the local derivative of this addition operator is nothing but just one, right? Because adding plus one doesn't really change the derivative. So, in this case, negative 0.53 will be multiplied by one, which is still negative 0.53. Exponential, we know that the derivative of an exponential is exponential itself, right? So what happens is, this gets multiplied by the value of exponential, which is 0.37, right? And then we get negative of 0.2. And, we basically repeat this process, for all the nodes. And as a result of that, we get, negative 0.2, 0.39, negative 0.39, negative 0.59, and 0.2, okay? As a result of computing all this. You can feel free to validate this. I think, you'll have no problem taking the derivative of this equation. I mean, it will take some time because there are lots of terms, but, after you, derive all this, then you will see that the values that I produce over there is exactly the same as the values that you analytically compute. Okay. And remember, backpropagation is just the implementation of the chain rule. So these are not even approximate gradients. These are the exact gradients. Okay. That is free of, up to numerical error. Okay. So putting this all together, what we do is, we construct a neural network, right? And a neural network itself is a computational graph. We have neurons that gets aggregated, so there's an addition node, right? And then there's an activation function, and then we pass along the information like that. So that's the forward pass. And after we construct the computational graph, we calculate the loss function. And from that loss function, we backpropagate the gradients, okay? And as a result of that, no matter how complicated your model is, you should be able to compute the gradient of your loss function with respect to the weight values of your model, using which you can then update your model, right? Because the gradient descent algorithm is simply, saying that you can take the gradient of the loss function with respect to model weights, and then you just update the model weights by using that gradient, is essentially what gradient descent is all about. So no matter how deep your neural network is, or no matter how complicated your neural network is, that's essentially what you need to do. Okay. Now, in 1986, when the backpropagation algorithm first came out, yes, theoretically it was possible. But then, still, neural network was not a thing because mostly, hardware limitations. And around, 86, there was already this algorithm called, support vector machines, which was much simpler and easier to implement. And then the idea of having this crazy, connectionist approach was kind of still a, very minor idea. So, it was perceived to be a, not so practical algorithm, back in time. Another thing is, this is a hard drive, back in 1950s. And the hard drive, which is about the size of, I don't know, a cabinet or something, could only store 5 megabytes. So 5 megabyte is like, I don't know, like the photo that you upload on Instagram is easily 5 megabytes or above, right? And, you're required to have that, giant machine to store that, one image. So obviously, because of the hardware limitations and, things like that, neural networks were not that popular. But then, this came out, NVIDIA. I personally credit them a lot when it comes to the deep learning revolution. The idea of general purpose GPUs came out around 2009 or something. And then, computer graphics, like computer games, when you play them, inside of the graphics card is a bunch of matrix multiplications. So when you have a high quality graphics, like when you play a computer game, those graphics engines basically do a lot of matrix vector multiplications. Around 2009 ish, people kind of realized, oh, if computer games are nothing more than matrix vector multiplication, we could use it for some scientific purpose instead of just computer games. And that's the idea of GPGPU, general purpose graphics processing units. And then NVIDIA around that time released this engine called CUDA, C-U-D-A. And CUDA engine allows you to program, some high efficiency, parallel codes on GPU. So back then it was C++. Now CUDA is available in Python wrappers. So PyTorch, for example, is built upon, CUDA acceleration. And what happens is, all these matrix vector multiplications are done inside of a GPU. So that was kind of the idea of GPGPU. Another important, I think, breakthrough that we have to credit is this thing called the ImageNet. So ImageNet is a collection of digital photographs where the whole ImageNet data set is comprised of 14 million images that are annotated with some image labels. So there are lots of animals, for example, cats, dogs. Oh, okay. Are we on time? All right. Well, do you want me to wrap up? Okay. Well, so just briefly, ImageNet is comprised of lots of image data with labels indicating what's inside of that image. And a group of Stanford researchers came up with this ImageNet data set. And not only did they, come up with this high quality data set, but also they, opened it to public and then hosted a competition. And the competition, the ImageNet competition, was basically like, whoever submits a machine learning model that has the highest accuracy in classifying those images, becomes the winner. Was the idea. So a subset of that original 14 million, so about 1.4 million images, with 1,000 different classes, were publicly, made publicly available. And then, that competition started back in 2010. And then, it lasted a little less than a decade. And then since the third competition of ImageNet was, this idea of convolutional neural nets and deep learning. And then, compared to, when the neural network first came around, we had lots of data with NVIDIA GPUs. So, people were able to, train much more serious, much larger, neural network algorithms. So that's, kind of what happened. In tomorrow's class, we're gonna be, looking further into, the ImageNet competition a little bit, alongside the intro to convolutional neural network, which is a specific type of neural network that is specializing in processing images. And then hopefully we'll have a chance to play a little bit with PyTorch and actually code ourselves a simple neural network model. So with that, thank you so much, all, and it was really fun. And I'll look forward to see you again tomorrow. Have a good night.
Thank you.
So, he must be feeling tired, right? So he is waiting outside. Just grab